Welcome, everyone. I'm excited to kick off our presentation today on the fascinating topic of matrices. This is the first slide, so I just want to briefly introduce what we'll be exploring. We'll cover the basics of what matrices are, their importance, and how they're used in various fields. So let's get started and dive into the world of matrices. Let's move on to slide 2, where we focus on the order of a matrix. The order of a matrix essentially describes its size, which is determined by the number of rows and columns it has. For example, if you have a matrix with 3 rows and 4 columns, we call that a 3x4 matrix. Understanding the order is fundamental because it helps us determine how matrices can be multiplied or added, ensuring the operations are compatible. Keep in mind, the order also gives us a quick snapshot of the matrix's structure, which is crucial when working with multiple matrices in more complex calculations. So, recognizing the order helps us keep everything organized and make sure our matrix operations follow the rules correctly. A matrix is essentially a square or rectangular arrangement of numbers, and we write these numbers within square brackets. The key idea is that these numbers are organized in a definite order, specifically in rows and columns, which makes matrices very structured and easy to work with. The concept of matrices was introduced by a renowned mathematician named Arthur Cayley back in 1857. Since then, matrices have become a fundamental part of mathematics, finding wide-ranging applications across different fields. Whether we're dealing with systems of equations, transformations in geometry, or computer graphics, matrices serve as a powerful tool. So understanding what a matrix is and how it's structured is really the foundation for exploring many advanced topics in mathematics and beyond. Today, let's look at the order of a matrix, starting with an example. The order of matrix A is 2x2, which means it has 2 rows and 2 columns. Now, in general, when we talk about the order of any matrix, if there are R rows and C columns, then we write the order as R by C. So, for any matrix, knowing the number of rows and columns helps us understand its size and structure. This concept is fundamental because it sets the stage for more advanced topics like matrix operations, where the order determines whether operations like addition or multiplication are possible. So, always remember, the order gives us a quick snapshot of the matrix's dimensions and helps us ensure we're working with compatible matrices in calculations. Let's take a closer look at the different types of matrices we've discussed. First, a unit or identity matrix is a special kind of diagonal matrix where all the leading diagonal elements are equal to 1. It's usually denoted by the symbol I. This matrix plays a key role because multiplying any matrix by the identity matrix leaves it unchanged, much like multiplying a number by 1. Next, we have the null matrix, also known as the zero matrix. This one is quite straightforward. All of its elements are 0. It's useful for representing the absence of any value or influence in matrix operations. Moving on, the scalar matrix is a diagonal matrix where all the leading diagonal elements are equal. But unlike the identity matrix, these elements can be any number, not just 1. This type of matrix is important when scaling vectors or other matrices uniformly. Then, we have the diagonal matrix itself. This is a square matrix where all elements outside the main diagonal are 0. The main diagonal can contain any values. Diagonal matrices are particularly easy to work with because their multiplication is simple and efficient. Speaking of square matrices, these are matrices where the number of rows equals the number of columns. This property enables many important operations, like finding determinants and inverses, which are central in solving systems of equations. When a matrix has only 1 row, it's called a row matrix or row vector. Conversely, if it has only 1 column, it's called a column matrix or column vector. These are fundamental in linear algebra because they represent vectors in different orientations. Finally, a rectangular matrix is one where the number of rows and columns are not equal. These matrices are common in real-world data, where the dimensions often don't match, and they require different approaches for analysis. By understanding these different types of matrices, we get a solid foundation for exploring their properties and how they can be applied in various mathematical and real-world contexts.